Hello, this is Ilianos, and in this video we're going to solve question 3 from the 2021 AP Electromagnetism exam. This is the exam paper. We can scroll quickly to question 3. We're going to go through the list of rules and constants and calculus tips and the answers for part 1 and part 2 that we have seen in previous videos. Alright, and here is question 3, where we see a ring and a magnetic field. Now what I guess is that the ring will be rotating or the magnetic field will be changing, so we're talking about a problem with electromagnetic induction. Let's see what we know. We have the ring of area A, resistance R, and the magnetic field varies with time. So we need to derive an equation for the induced current, and we need to know that the current is EMF over R. But before we go to this, we need to find the induced EMF, and the induced EMF is from Faraday's law minus number of turns multiplied by change of magnetic flux with respect to time. So first we need to find the magnetic flux, the expression for magnetic flux, which is B times area times cosine of the angle between the magnetic field and the normal to the plane of the loop. Now the magnetic field changes with time, so it is beta over t multiplied by the area that it is given as a value, and the angle is 0 degrees, so cosine of 0 we can ignore it. It is equal to the unit, it is equal to 1, so we can ignore it. So the magnetic flux is beta times area divided by t. So the EMF is one term only. So, and if we're talking about the values, the magnitude of the induced current, we don't need the negative. So number of turns, which is 1, multiplied by the derivative of beta times area divided by the t derivative. Now the derivative of 1 over t is minus 1 over t squared, but again we're talking about the value, we're talking about the magnitude here, so it is beta times area divided by t squared. And now that we know this, we can easily find the induced current, so it is beta times area divided by t squared, and again divided by the resistance. So this is our final answer for the induced current. Then we are given the values of beta, area and resistance, and we need to find the electrical energy from time 1 to time 2. Since we need the electrical energy, probably we'll talk about electrical power first, and well, for the power, the definition for power is derivative of energy with respect to time, so this is what we will use. But first we need to calculate an expression for the power. Since what we have here is the current, we're going to use the expression I squared times R. So beta times area divided by t to the power of 2 times R, all of it squared multiplied by R. So beta squared, area squared, time to the power of 4, R squared, and again multiplied by R, so we'll only have 1 R on the denominator. So we can use this for calculating the energy. D is equal beta squared, area squared, t to the power of 4, R multiplied by dt. And since we need to find the energy, it will be integration of these values. So from 1 to 2, the beta is given, so 0 to the power 0.5 to the power of 2. The area is again 0.5 to the power of 2, the time to the power of 4, and the resistance is 2 multiplied by dt. Now we'll need to go to the calculator for this. Integral from 1 to 2, 0.5 to the power of 4 all of it divided by x to the power of 4, and then multiplied by 2. This will take a little bit of time. We'll see it in 1 minute. My value is 9.1 times 10 to the power of -3. And because it is energy, the result is in joules. Okay. We can continue to part C, where we see now that the ring has turned a little bit, but we have the same magnetic field, beta over T to the power of 2, and we need to figure out if the energy is more or less or the same. Now, what causes does this change bring? The fact that the ring has turned will result in less magnetic flux, since there is an angle now, the angle now between the normal to the plane of the loop and the magnetic field is 60 degrees, so cosine of 60 is less than 1, so we have a smaller value for the magnetic flux. And since there is a smaller value for the magnetic flux, this means that the induced current and the induced EMF, the I induced, will be less. And since the induced current is less, the power will be less. And since the power is less, the energy is less. So we will have less energy, and we need to explain this with a few words or with a list of the rules that we used in the previous part. So basically we'll say that the angle between the magnetic field and the ring causes smaller value for the magnetic flux. This will result in less induced current, this will result in less power, and since the time interval is the same from 1 to 2 seconds, this will result in less dissipated energy. And now we go back to the previous situation. We know the area, the resistance, I think nothing changes, and we see that, okay, actually there is an axle through the ring, so the ring is rotating, and this causes an induced EMF that changes depending on the position. Either we'll have maximum current, maximum EMF, or we will have zero EMF. So basically we'll have an alternating current. And we need to figure out what is the angular speed of the ring. Now, we'll have to go back to grade 11 from this. We have to go back to mechanics and simple harmonic motion. We cannot find the omega directly. However, we see that the period of this oscillation is 2 seconds from the graph. So we say that the period is 2 seconds, so the omega is 2 pi over period, so 2 pi over 2, it will be equal to pi rad per second. On the easy side, and we need to calculate the maximum EMF, the maximum induced voltage on the ring. Maybe this will take a little bit long, but we need an expression for the magnetic flux, because the EMF is minus number of turns multiplied by the derivative of the magnetic flux. So the magnetic flux is B times A times cosine of the angle. Now the B doesn't change, the B is constant, 0.5, and the area also doesn't change. The area is again 0.5, but as the ring is rotating, what changes is the angle between the magnetic field and the normal to the loop. So we have a cosine of the angle that changes with time. And if we remember, the omega is angle over time, so the angle is omega times t. So cosine of theta, it means cosine omega times t, which is very, very similar to the expression that we knew from for simple harmonic oscillation for the position, which was A times sine or cosine omega t, and so on. So this will be 0.25 times cosine of pi multiplied by t. And for the EMF, we need to derive it. So the EMF, it is minus 1 multiplied by the derivative of this, which is the derivative of the cosine, so 0.25. The derivative of cosine omega t will be the derivative of the quantity inside the bracket, so just pi, multiplied by sine omega t, so sine pi times t, and the derivative of cosine is minus sine, so we'll get a plus here. Now, the value in front of the sine is the maximum EMF, and the sine of pi t is variable, so the EMF max is 0.25 times times pi volts, or you can just say 3.14 divided by 4, this is 0.78 or 785, so 0.79 volts. Okay. Now, the ring begins to rotate at an angular speed 2 omega, so the ring begins to rotate faster. And on the graph below, we need to draw a curve that indicates the new EMF. Okay, since the since the ring will rotate faster, for sure the electromotivating force, the new voltage, will be greater, and since the speed is doubled, the EMF will also be doubled. So from 0.79 will become 1.58. So the EMF for sure will be doubled. However, we have to be a little bit careful now, since the ring is rotating faster. It will rotate, it will finish one complete rotation in less time. So if it needed 2 seconds in order to rotate once, now it will need less than this time. It will need half of the time, so it will need 1 second to rotate once. So not only will have a greater EMF, but it will have a squeezed graph. So before one complete oscillation took 2 seconds, now one complete oscillation will take 1 second, but we need double the EMF. So somehow like this. A little bit better. We need double on the top and half of the before, and double on the bottom. So somehow like this. And carefully, we're gonna try to plot exactly the same for this part and exactly the same for the part between 2 and 3 seconds. So again, the key points that we need to be careful here is, again, for sure double EMF, but at the same time faster rotation, so half for the period. Justify your sketch. So we need to mention this. The EMF is what we said before. It was B times A times cosine of omega t. Okay, this was the EMF. All right. Actually, sorry, this was the magnetic flux. The EMF was B times A times omega times sine of omega t. Since the omega is doubled, the EMF will also be doubled, but the rotation will be faster. The sine omega t the quantity inside the sine will increase, so the sine omega t as a periodic function, it will have a smaller period, so smaller, less period. Half period. If necessary, we'll justify it to the fact that the omega is 2 pi over the period, so the period is inversely proportional to the omega. Okay, and this is our final answer. That, in my opinion, was a quite nice question. Not so difficult, but on the smart side. Feel free to comment any questions that you might have or any suggestions for the channel. I hope you enjoyed this video and thank you for watching. Have a good time.